So corresponding to a random variable, we had discussed two functions. One is called as PDF, that is, so for discrete random we have PMF, and for continuous we have PDF. So PDF we have not discussed yet, so we'll discuss it once we go to continuous random variable. So right now we are in discrete random variable. So in that we have discussed two functions. One is PMF, that is probability mass function, and CDF, this is cumulative distribution function. Just a recap, I'll summarize the properties of PMF and the CDF. So what PMF is, so in PMF we assign probability to the events. So we have a random variable x, suppose x takes some value a, b, c, d, something of that sort. So probability x is equal to a, this is defined as PMF for all of these values. This is what we call as PMF. What are the properties of PMF? The first thing PMF is probability. It is written like this, or it can be also written like this: probability x takes value x. This should always be non-negative. It should be greater than or equal to 0. So this is because of axiom of probability. Then the second thing we saw is that if you sum up all of these, if you sum up over all the x's, if you sum up all the x's, this should be equal to 1. But I wrote it like this: union of p of x is equal, let's suppose ai, I goes from 1 to n. If we have n values, that is taken by a random variable, so this should equal to 1. So this was property 1, and this is property number 2. Whenever you, why am I mentioning these properties? Because whenever you are constructing a PMF, suppose you are given a random variable, or you are given a question in which you are asked to find a distribution, what you will do is you will either resort to CDF or PDF or PMF in the case of this discrete random variable. So what you have to do is you will have to check these two properties. If you are constructing PMF, are they abiding these two rules? Are they non-negative? Is the sum equal to 1? Okay. And it's only defined for specific points. Let's suppose PMF is defined for distinct values of x. So for anywhere in x which is not in the range, so we assume this to be 0. So P of x is equal to x is equal to 0. So I'll call this is 0 for outside range, for outside the range. Why am I talking about range and domain now? Because you know the random variable is a function. So if it's a function, so it must have a domain and it must have a range. So PMF is only defined on this distinct point. So for any value x that is not in its range, so probability mass function will be equal to 0. Okay, and this is actually assigning the probability to an event. So if you see this, so if I write probability of x is equal to a, so this over here is an event. As I said, what you have to do is, if you have this value, you go to sample space and see how many of the outcomes in the sample space can be tagged under this. So collect all those outcomes, so that will be that will constitute an event. So this is an event. So this is about PMF. Then we also studied about CDF, and we also saw the applications of CDF. So CDF was denoted something of this sort: P of x takes value, let's suppose, less than small x, something of this sort. Or it can be also, sometimes it's also written like this: f of x takes value x. This capital F is denoted as CDF. So if you see books, either this is the notation or this is the notation. Okay, again, so this should be between 0 and 1. Okay, and then we said second property is it should be non-decreasing. It can be constant at some places, but it is usually non-decreasing. That is, it will always increase, and sometimes it might be constant, and this is called as monotonicity. And then one more important thing is it is right continuous. All of these things are applicable on functions, and you know CDF is a function. So we have seen previously that CDF of a discrete random variable is a step function of this sort. Let's suppose we have this and this. Let's suppose something of this way. And then it is right continuous. So you can put it like this. So why is it right continuous? So let's suppose, what is meaning of right continuity? So I assume that you at least have some understanding of what continuity in function is. So simply, if you see there are certain jumps over here. So if you find the value of function at this point and find the right hand limit, so you will see the right hand limit and the value of the function at that point is same. That's why it is right continuous, not left continuous. So if you find the value of this function at this point, and if you find left limit, they won't be equal. Okay, that means it's not left continuous. So it is right continuous. In general, it's not continuous, but it's just right continuous. And one more thing is that if you go to negative infinity, if you, let's suppose, move on to this negative infinity, so you will see that this f of x it tends to 0 while you go to negative infinity. So negative infinity basically means if you go to the least value possible, why do you start from it? So it will tend to 0. Sometimes it is not exactly 0, that's why I am writing tending to 0, but sometimes it goes to 0. And the vice versa is if you go to positive infinity, if you go from here positive infinity. So because we are accumulating the sum, and you know the probability is between 0 and 1, so for sure the probability should tend to 1 when you go to plus infinity. Okay, this is the behavior in extremes, and you should know that this is a step function in terms of discrete random variable. It's a step function, and we know what is the relation between CDF and PMF. So we have f of x is equal to, you sum the PMF. So PMF is written like this. Let's suppose you sum it for this. A goes from 1 to something. You can just write, I think intuitively you understand this. So this is just a recap what we saw previously, so as to get in the same page. Okay, now let's move ahead with the next topic. Okay. I'll quote a very important result. So before quoting that result, so if you see how we started the random variable. So in that random variable, I said, let's suppose random variable is a function. So if I have a set of students, so I have, oops. So if I have a set of students, give me a little bit of time. I knew this camera was going to give me some issues today. Okay, so if you remember the previous session in which we discussed, one of the problems discussed in the, I think, first session was that we were taking a set of students. So in that set of students, we're sampling them randomly. Let's suppose we have student S1, S2, S3, S4, and so on. And then I said these random variables can be thought as functions. And you have a function, let's suppose you take student 1, and then you have some function, let's suppose weight. And similarly, you have some other function height. You can give these students as an input, you'll sample them randomly, give them inputs to these two functions, and they'll give the corresponding values. So we'll take S1, it will be given, let's suppose, weight of say 70 kilograms. Similarly, S2, the weight will be some 85 kgs. And if you give this to S1, so it will give height of 1.7 meters. S2, let's suppose 1.8 meters, something of this sort. So now you know that these two functions can be clubbed together, and we can compute BMI from this. Okay, I don't know exactly how BMI is calculated. Let's suppose this is weight divided by height square or something of this sort. So now this also is a random variable, okay, because this is a function also. So what I'm saying is, if you have a random variable, so if you have some other random variable, now if you make a function out of these two random variables, so the other thing, that function that you make because of that is also a random variable. And now, because we were studying binomial and Bernoulli random variables, let's suppose we have two random variables. Okay, this is the result that we'll discuss for maybe next couple of minutes. We have two random variables, x and y. Okay, and both follow binomial distribution. So how can we write that? So we'll write x follows binomial distribution with n and p, because you know there are two parameters. Similarly, y follows binomial distribution with m and p. Now both of these follow binomial distribution. If you add these two, random variables, so this also follows binomial distribution with m plus n comma p. Okay, the restriction that here is this probability should not vary. This p should not vary. So if it varies, then we cannot write this result. Okay, so and the other thing is both of these should be binomial, then only I can write this binomial p. Okay, it can be directly seen as a function. So how do we compute addition of functions? Let's suppose you have function f1, you have function f2. So if they are defined on the same domain, so if the domain is same, here clearly the domain is same. You do these trials. Okay, you can think this of, you have coin flips. So in the first case, x is a random variable in which you do n flips, and y is a random variable in which you do m flips. So I'm saying that now if you do m plus n flips with the same p, so this should sum up to this. How do you add these functions? If you have function f1, if you have function f2, so you evaluate function f1, let's suppose, on x, and then you evaluate function f2 on, let's suppose, x2, this is x1, say, and then you add the results together. Okay, that's how you get x1, x2, something of this sort. Okay, so similarly in here, this is proof that I just gave you by giving some verbal description, that you have initially n trials and then you have m trials. So in the first case, this is what will be followed. In the second case, this is what will be followed. So you can think this as a single experiment in which we had m plus n flips, m plus n tosses, and then it should follow this binomial of n plus m comma p, but under the constraint that we should have. This is giving me a lot of trouble today, I don't know why. This is one way you can think of this. So you can think this x and y as two functions. So if we have in the x variable you have n flips, and in the y variable, random variable, you have m flips. So in the first case, this is what the distribution is followed. In the second case, this is the distribution that is followed. So if you now consider them as a single case, that means you have m plus n flips. Okay, then by default you can clearly see that this m plus n can be thought of the number of flips, and the probability p remains the same. Okay, the second way of looking at it is by using the indicator random variables that we saw in the previous session also, that you can also see this distributions by using these indicator variables. So how to do that? So now you have this x, you can see x1 plus x2 and so on till xn. So these are x1 and x, basically xi's, these are known as indicator random variables. Okay, and they are 1 for a success, and they are 0 for failure. Can be also seen as this. So now if you see this x, if you see that suppose we have this x, so x can be thought like this, y can be thought like this, y1 plus y2, yeah, y1 plus y2 and so on till yn, something of this sort. So now you know this is this says number of successes in n trials, and this is number of successes in m trials. So now we can write both of these together. So we can write them like this, x plus y can be written like this, x1 plus x2 and so on till xn, plus y1 plus y2 ym. I think they should be ym, because here we have m trials. So now if we put both of these together, now you know that I can write both these as, this is number of successes in n trials, number of successes in m trials. So I can write this as binomial of x plus y comma p. So this is by using the indicator random variables, and but there is a formal proof also. You can formally prove it. I'll just show this proof so as to show you power of conditioning, and how can you use the conditioning that we have studied in the previous sessions in order to prove things. So the point that we have to prove is, we have to see that this p, this binomial of x plus y comma p, it is actually a binomial distribution. So if I have these two random variables x and y which are binomially distributed, then if I see this x plus y comma p, it should also be binomially distributed. So how to prove that? Basically, I want this probability of x plus y. This should be binomial distributed. I should get a binomial description of this. So let's suppose we want k successes out of these. This is what I have to find. Probability of x plus y is equal to k. I have to see from m plus n flips, I should get k successes. So I want a form like this. So I should have binomial coefficient, then some p to the power something, q to the power something. So I should formally prove it by just assuming that x and y are binomial distributed. So I can expand this by using law of total probability, or by I can use by conditioning. I said conditioning is like wishful thinking. If you want to wish something, just condition on it. So I can condition, let's suppose, on x. I can say, so this is like an event of this sort. I can say that I'll use law of total probability and condition it. This will be equal to p of x plus y is equal to k. Let's say I'll assume given x is equal to I. Let's suppose this, and multiply probability of x is equal to, and this is actually summation. So I am summing this over all the I. Okay, this is breaking this x plus y like this, and giving that we are conditioning on x is equal to I. This is because of law of total probability. Law of total probability. Okay, now what I can do is, so now I know given that x is equal to I, so I can put the value of x is equal to I over here. Okay, so I'll get the value of y. So I'll say summation of p of and y If I put x is equal to I over here, so y is equal to k minus I. K minus I given x is equal to I. Probability of x is I. To stop me if you don't understand a step. Okay, these things are very important, Sanders, because to perform algebra by using the tools that you already know becomes a skill after a while, because now you have tools and you just need to use them to prove something. Okay, this is what we are trying to do here. Now if you see this, both of these are independent. This x and y are independent. Now once I saw that, once I see x is equal, given x is equal to I, it should tell me nothing about y. So this basically means that this should be equal to probability of y is equal to k minus I, because this condition should say nothing about this y. Initially I use this condition so as to just get the value of y. Now I'll just multiply with probability of x. So why did I do this? So this was done because I just needed, I know probability of y and I know probability of x, because I know both of these are binomial random variables, and I can use binomial theorem. When I know both of these follow binomial distribution, so what I can do is I can just put these values over there. So I can say, so in this I need k minus I successes. Okay, out of, so y has m trials, so in here I need I successes, it has n trials, so I can just expand them by using binomial theorem. Let me expand that. So this is equal to n choose k minus I, m choose k minus I. Okay, probability of success, let's see, because both of the probability is p, probability of success is p, and I need k minus I, and q is m minus k plus I. Okay, this is for this part. Then multiplied by this part. I'll again use a similar word. Just n choose I, p of I, q of n minus. Is this clear so far? Till here, is it clear? Any questions still here? Now we have reached the result worry. If you see this, I can club these terms together. Let's first do this summation of I goes from 0 to k, m k minus I, n of I. And then if I put these two things together, so this is p and p, so bases are same, power should be added, so this is k minus I plus I, so this is p of k, and this is q, so this is m minus k plus I, this should be plus n minus I, so I and I will get cancelled, so we'll be left with m plus n minus k. So this portion over here, this is called as van der Waals sum. So this is equal to, this over here is equal to m plus n, choose this portion, the one I have underlined with the purple. This is equal to m plus n, choose k and p of k and q of m plus n minus k. So we were finding probability of x plus y is equal to. Now you see that this is actually binomial distribution, because the PMF that we got, this is PMF that we got out of this, and binomial thing. So if you see, this is m plus n by k, so if you add these things, k plus m plus n minus k, so this will be also m plus n. So it is like n choose k, so you had p to the power k and n minus k, so this is similar to that. Now we need to see this, so this portion over here, so we need to see how is this equal to m plus n choose k. Okay, so before going to that, I'll show you one proof method that is called as story proofs. Sometimes algebraically it is tedious to prove things, so but if you if you make a story, or if you just follow logical deduction, then you'll clearly see that this can be like, if you just think about these things, and then you can make a story out of that, and you clearly see that the proof is followed by the story. So I'll name them as story proofs, not my name, it is from a Harvard professor. And let's suppose we have this, we have n choose k. Okay, so this is also equal to n choose n minus k. All of you know this result. Let's suppose if you have 4c, let's suppose if you have 10c3, you know that this is also equal to 10c7. You can formally prove this by using algebra, n factorial divided by n minus k, this and that. But how you can think about this? So this is basically, let's suppose you have n people, or you have some n items. So these are n items. So this is a story proof. We are constructing a story, and based on that story, we'll try to see that left hand side is equal to right hand side. So now what I'm saying is, let's suppose you have n people. So if you have to choose k people out of them, so among n people you are choosing k people, so you are left with n minus k people. Isn't it also similar that you will choose n minus k people and you will be left with k people? This is a symmetric problem. So if I have, let's suppose 10 people if I am choosing 3 people, because I know from that group I am now left with 7 people. So it is same. It is basically leaving 7 people. It can also mean that we are picking those 7 people and leaving other 3 people. This problem is symmetric, so you can directly see from this story both of these should be equal. If you choose k from n, or if you choose n minus k from n, this is one and the similar, because you are choosing one thing and leaving other thing. So this is choosing and leaving, so you can just label them differently. Now whatever you left earlier, you can call I chose them, and I left the first group. So this is basically dividing the group into two things. So left and you choose. So it can be thought as reverse also. The one you chose initially, you can left them, okay, and the one you left initially, you can choose them. So the problem is symmetric, and this is a very rigorous proof. So this is a proof accepted in mathematics. You don't have to write algebra. If you just write a story which makes sense and it follows from logical deductions, there is no hand wavy thing in there. So this is a proof without algebra. So whatever story I said, so if this thing came up, if you write that thing as a proof anywhere, so this will be considered as a mathematical proof. Let's see now second thing, which is this is very easy to prove algebraically, but there are some things which are very hard to prove by using algebra. So if you can consider a story out of that, so it becomes very easy. Let's suppose I'll write this. So you have n into n minus 1 k minus 1, and then this should be equal to k and ck. Okay, so how is this equal? So even you should not memorize these things. I'll tell you the way, so how I remember them, and then you can also use those tricks to remember it. So let's suppose you have n people. So you have n people. So out of these n people, you have to choose k people, and among these k people, one should be designated as president. Designated, let's suppose, as president. So if this is the problem, let's suppose this is the problem. You have n people. Out of those, you have to choose k people, and one has to be designated as president. So now you can think this problem in different domains. You can initially choose a president out of these n people. So there are these n ways. So you are choosing n people for a presidency. Okay, once you have chosen a president, then you are left with n minus 1 people, and out of those you have to choose k minus 1 people. So this is the second factor. You are choosing the president first. So this is president, and then this is choosing k minus 1 out of n minus 1. Similar, this thing can be thought as reverse also. You can choose k people out of n. So you are choosing k people out of n, and among those k people, now you are choosing a president. So this is that k. Choosing a president is the second step now, and both of these things are equal. Now you try to prove it rigorously. It will at least require 5-10 minutes of your time. So now if you understood this, so I am telling you to try to do it algebraically. It will at least take 5-10 minutes of your time. Okay, and this is a very rigorous proof and an accepted proof. Nobody will tell you that you are just giving hammering argument. This is an accepted proof. And the third thing that I'll prove is this Vandermonde. This Vandermonde sum, in which we said that if, let's suppose, we have m plus n choose k, this is equal to summation of m choose I and n choose k minus I, something of this sort. Okay, so consider it like this. So let's suppose you have this sometimes also called as Vandermonde's convolution, because we have this plus word there. So this is called as Vandermonde's convolution, because x plus y is actually in convolution operation. Okay, and we'll see it in detail once we go deeper into probabilities. We'll see what this convolution means in terms of probability. Let's suppose now you have this. So you have this left hand side, m plus n choose k. So let's say you have two groups of people. So if you have to again prove it algebraically, it is a bit tedious, not difficult. It's a tedious. You have to keep track of a lot of calculations, and then it will take a page or more than a page to prove it algebraically, because you will open this side and then you will open this side and then concatenate terms together to see left hand side is equal right hand side. So again here we'll give a story proof. So now you have m plus n choose k. So what I'm thinking is like this. So you have two groups of people. It cannot be people, it can be any generic setting. So I'm just taking people. So you have two groups of people. Let's suppose you have two groups of people, in which one group has m people and another group has n people. So you have m group of people and you have n group of people. Now in the first case, what are you trying to do is you are trying to choose I people in this, and you are trying to choose k minus I people. Basically in total you want to choose k people in this. So the first hand side is directly you are having m plus n people. Consider both of these groups. You are choosing k people out of them. So this is that left hand side. Now the right hand side, how can we evaluate this? So from the first group you are choosing I people out of m people. So this is that, choosing m people out of I people. and then from here you are choosing k minus I people out of this n people. But you know now know that this I can vary. So this let's suppose this I can go from 1 to k. So this can go from, let's suppose, if you can choose, let's suppose 0 people from here, all the k's from here. You can choose 1 person from here, k minus 1 from here. You can choose 2 people from here, and you can choose k minus 2 from here, something of this sort. So this I will go from 0 to k in here. Okay, that's why you are summing them up. So here this is again a rigorous proof, a story proof, in which we constructed a story. Left hand side, we are treating it as a group of 2 in which one set has m plus n, and you are choosing k people out of these m plus n people. So right side we have 2 groups. So this is the first group and this is the second group. And now we know that there are a lot of possibilities how you can choose. You can choose 0 and k, 1 and k minus 1, 2 and k minus 2. That's why I am adding these summation terms because of that. Okay. Any issues with this proof? So if you see this over here, the one we proved, the last thing, that is Vandermont's convolution. So we use that in this proof where we were proving formal proof of this binomial. Okay, I told you 2 things. So why am I introducing you to this proof? The first rationale behind showing you this proof is that you can use the previous concept like conditioning, log total probability to prove other things. Second thing is there are different ways and there are beautiful methods in which you can prove things without even writing algebra, tedious algebra. So these things are called as story proofs. So I showed you a couple of examples and we used one among them, that is this Vandermont's convolution. Okay. Now sometimes what the problem becomes that you are given a problem and you mistakenly can assume that it's a binomial distribution or the random variable follows binomial distribution, where it's not the case usually. Okay, I'll give an example and I'll ask you to evaluate it. I'll see if you make the same mistake. Now I have given you the prior that I am giving a question in which people usually mistake it as a binomial probability, but it is not binomial probability. You will have to tell me what probability it is. Then you have to construct PMF. Okay, so let me clarify first few things. So if it's a binomial with n and p, so we are considering that each of the trial is independent. So the trials are independent. So this is the first assumption. Whenever you see something which is following binomial, you clearly see that each of these is a Bernoulli trial and the trials are independent. And second thing is p is constant. This probability is not varying. So when you perform these trials, it is not the case that this p is varying in the first, let's suppose, toss, or in the first flip the p was something, and the second flip the p changed. Then there is a high possibility that that distribution or that random variable or that process will not follow binomial distribution. Another question goes like this: you have 52 cards in a deck. So you have a deck of 52 cards in which you are giving 5 cards. You are giving 5 cards to a person at random. Okay, and this is without replacement. Without replacement. That means if you are giving 1 card and then that person gets that 1 card, and second time you are not putting that card back. You are again giving the second card, which is no, the first card is not included in the deck. So this is without replacement. So you have 52 cards in a deck, and out of these 52 cards without replacement, you are giving 5 cards to a person. Okay. Now what you have to do is, because you know that it has 4 aces. Okay. Now let's suppose x is a random variable which defines aces. So x defines number of aces. This is a random variable. X is a random variable which defines number of aces. Okay. So can you construct PMF for this random variable? For number of aces, can you construct PMF for this? So now if you see this x is a random variable now. So random variable takes some values and we know that this is a discrete random variable. So this is number of aces. So if there are 4 aces, the possible values for this x are 0, 1, 2 and 3. 0 can be aces, 1 can be ace, there can be 2 aces, 3 aces or 4 aces. There can be 4 aces. 0, 1, 2, 3 and 4. So these are the possible values which this random variable takes. In order to construct its PMF, so we should be constructing probability of x is equal to 0, probability of x is equal to 1. That means probability that there will be no aces, there will be 1 ace, and so on. Probability x is equal to say 4. And let's suppose we'll do it for probability of x is equal to 3. That means out of the 5 cards that we have taken out of that 52 card deck without replacement, we should have 3 aces out of these 5 cards. So now we will use naive definition of probability. That means total and favorable. So favorable divided by total, assuming that everything is equally likely. So how can we compute total? So we are computing it. We are taking 5 cards out of 52 cards. So we can say 52 choose 5. So this is the total number of combinations possible with 5 cards when you are just taking these 5 cards out of the deck. And now we have to compute favorable conditions in terms of 3. So you want 3 aces. Now this card, so you have card deck of 52 cards. So there are 4 aces and there are 48 non-aces. Now you have to choose 3 aces out of these 4 aces. So you can choose 4, you can choose 3 aces out of these 4 aces. So 4 choose, 3 choose 4. And then what you can do is, because now you are left with 48 cards. So out of these 48 cards, you have to choose 2 cards, because in total you have to choose 5 cards. Okay, so this is the probability that x is equal to 3. That is probability that the number of aces in the 5 cards is 3. So favorable are these many and total is these many. Now we'll make it generic for k events. If we have to take k cards out of these, so probability of x is equal to k, that means a generic PMF function. So now I am saying 52, choose 5, and then here I'll be choosing 4. I'll be choosing k cards out of 4 multiplied by, I've left with 48 cards and I have to choose 5 minus k. 5 minus k. But given that this k is 0, 1, 2, 3 and 4, should not go above this. Okay, I hope you got that. So in here, this is PMF. This is the PMF that we're interested in. So now you saw that the first thing that you saw in this problem, that this is not a binomial distribution. Clearly, this is not a binomial distribution over here. And this is a PMF. Now, in order to check it's a PMF, so what can you check? That each of this has non-zero probability. And if you sum up this PMF, this should come up to 1. And this will be equal to 1. So this probability over here is called as, this random variable is called as hypergeometric. There's a separate name. This is called as hypergeometric random variable. So the difference between hypergeometric and binomial is that in binomial you are doing with replacement. Why with replacement? Because you don't want to change the probability. You don't want to change that p. If you are doing with replacement, then it becomes hypergeometric. And there is a relation between these, and you can clearly find mathematical relation also. But just in words, I can say that hypergeometric, in that you do these experiments without replacement. In binomial, you do it with replacement. If you just tweak the same problem a little bit, you just say, okay, I am taking 5 cards out of the deck, but with replacement. I am just taking 1 card and writing its number and putting this back in the deck. And then I am taking another card, putting it back in the deck. And then you can calculate how many number of aces will be there in, let's suppose, these many cards. And you can use directly the formula of binomial. Why? Because you are not now changing the probability. Each tile is now independent. It's not dependent on the previous tile. Okay? That is the difference between this geometry. Let's make this geometric a bit generic. We'll make it generic by having, let's suppose, an urn. So we have an urn or a basket in which we have red balls and we have blue balls. Let's suppose you have R red balls and you have B blue balls. So I'm saying let's generalize this hypergeometric distribution, our hypergeometric random variable. So how can you generalize this? Let's suppose you have an urn in which you have R red balls and you have a B blue ball. So total balls you have is R plus B. These are total balls. It is like the problem that we saw. We had aces and non-aces. You had 4 aces and 48 non-aces. So you have R red balls and B blue balls. So in total you have R plus B total balls. So let's suppose you sample n balls. You sample n balls without replacement. Without replacement. Now you are taking a ball, you are taking another ball, you are taking another ball. You are taking all of these without replacement. You are not putting the ball back into this. And now you can see over here, let's suppose x be the number of red balls or maybe white balls. You can condition anything. X is a random variable which is number of red balls. Okay. So you have to compute probability of this. So you have to compute the probability mass function of it. Can you compute it now? I'll give you maybe 5 minutes to think and come with the answer. So now you clearly saw that if x is this random variable, here we have number of red balls. So you should not confuse it with binomial, because here you clearly saw that it is without replacement. So it will become hypergeometric. So now we'll again use the naive definition of probability, total out of the favorable divided by total. So what is the total number of possibilities we have? Because we have R plus B balls. So out of these we are choosing n balls. So this is our total. This over here is total. And now we have to see favorable. because we are choosing k balls, because finding probability of x is equal to k. So now we should say we are choosing out of red these k balls. Okay, now we are left with how many balls? We are choosing n balls, and out of those k have been selected, n minus k, and total balls were r plus b. So out of these b balls, we have to now choose this n minus k. These are the favorable cases that we have. So this is the PMF of this is hypergeometric random variable. You can clearly see that when I'm writing these equations, even I'm just reading them in plain English. Okay, that is how the mathematics should be done. I'm continuously reading it in every lecture so that it gets to your subconscious. That whenever you see an equation, you have to read it like English, as if you are reading a poetry or you are reading, let's suppose, some book. You should read it like this. So here this is choose n balls out of r plus b total balls. Okay, and then you should choose r balls, to choose k balls out of these r balls. Now in total you are sampling n balls, so you are left with n minus k balls, and these n minus k balls have to be now chosen from the blue balls. Number of blue balls is b. Okay, this is favorable cases, this is our total cases, and this is the PMF. This is hypergeometric, and be clear here, we are doing it without replacement. That's what is making hypergeometric, not a binomial. So if it was with replacement, then we would have turned to binomial distribution. I hope this is clear. Okay, now you have a distribution. Okay, let's suppose you have some distribution. In order to completely tell me about this distribution, so you have to give me the PMF or CDF. In order to completely specify the distribution, you should give me PMF or CDF. If somebody tells you this is the distribution, so the question you should ask is give me a PMF or CDF in order to completely specify the distribution, so I understand everything about the distribution. Now sometimes it's not feasible to come up with PMF, CDF, or you don't want to go into tedious calculations. So you want some summary about the distribution. If you want summary about the distribution, and then you use some statistics. Let's suppose you use mean, you can use median, use mode. So all of these comes in with averages. You can find average. So let's suppose many of you here, let's suppose age, so age group. So I can say, okay, roughly what is the average age in a class, something of this sort. So I don't want to see the distribution. There is a distribution of ages. So I don't, you can't, let's suppose, give me PMF or CDF. You can give me though, but it's a tedious calculation. You have to ask everybody their ages, and then you have to say, okay, let's suppose x is a random variable, which is age of a student is a random variable. Then you can construct a PMF. Let's suppose from 20 we have these many people, for 21 you have these many people, 22 you have these many people. You can construct a PMF out of that. But in order to just get an idea which age group I am teaching, so I'll just ask you one thing: what is the average age in the class? It's something of that sort. So I just want a summary. I just want one statistic by the help of which I can just guess what is the audience here. So that is where these expectations, variance will come into the picture. If you want if you want summaries of these things, you just give let's suppose one number, or maybe two numbers, or maybe three numbers about the distribution, and you at least get some fair idea about what distribution is. So in that, we'll first see a summary statistic, that is expectation. The expectation basically is average or mean. Okay, average or mean. So but usually what we have is average is calculated when you have all the data points available with you. So if you have to compute average, so how do you compute? Let's suppose you have 1, 2, 3, 4, 5, 6. You have this. If you want to compute average of this, because you have all the numbers with you, so what you do is you will do something of this sort. You will just add them and divide by total number of observations. So you will do 7 divided by 2, that is 3.5. So when you add to all these, so you will get 3.5, because this is a geometric progression, this is an arithmetic progression rather. So I directly did first plus last term, and then I divided it by 2. Okay, so this is the calculation. So 1 plus 6 plus 1 divided by 2, so this is 3.5. So now what you can do is, if you do not have the whole data with you, so then you go to expectations. What is the expected value? So what can I expect? Okay, so let's suppose if I go outside, what is the weather I can expect? Okay, because this thing is a distribution. The weather is a distribution. You can just plot this distribution, but you can give me the value of distribution. If let's suppose this distribution follows some process, it follows, let's suppose, Bernoulli random variable, it follows Gaussian distribution, it follows some distribution. If you give me that PMF, maybe I can compute a value, but I don't want to compute values from PMF. I just want a ballpark figure. I just want a summary statistics. I just want a number by which I'll get some idea. As I said in the example, if I want to know weather outside, you don't need to give me the whole distribution. You can say me in the month of May, June, the temperature of Bangalore, let's suppose, is 30, 32, somewhere around that. This is the average temperature, is 32. So you just give me a number and I got a fair idea how hot or how cold it will be in the month of May, June. But it's not exact that if I go outside, I'll find it 32. This is the expectation I'll have. Okay? So that is the core idea behind expectation. You don't want to say something about the whole data, but you just want to get a fair idea. You just want to get an idea which is expected. That's why it's called expectation. The expectation means what is expected. So it is like average or mean. So when you have the full data with you, when you don't have full data with you, you resort to expectation. Let me show you one more way to calculate this average. So let's suppose I have 1, 1, 1, 1, say 1. I have 5 ones, and then I have 2, 3 twos, and then I have, let's suppose, 3. So how many things now? Okay. So if I want to compute average of this, so what I can do is I can say 1 plus 1 plus this, 2 plus 2 plus 3 plus 3 divided by 10, because there are these 10 numbers. So this is 5 plus 6, 7, 8, 9, 10, 11. 11 plus I think 6. So this is 17. I'll check my calculation if it is wrong. So this is 5, this is 6, this is 11. 11 plus 6, 17. This is 17 by 10. So the average is 1.7. This is average. This is how I can compute average. I added all these observations. Then what I did is I divided it with the total number of observations. So this is 17 by 10. That is 1.7. So now what I can do is, if I club these things into groups, because I have 5 ones, I have 3 twos, I have 2 threes. If I now club these things together, so what I can do is I can say something of this sort. I can say I have 5 ones. So I'll say this is in total, this is 10. So I should say 5 by 10 multiplied by 1, because I have 5 ones. In total I have 10, plus I have 3 twos divided by 10, total is 10 multiplied by 2, plus I have 2 threes. If I compute this, so if you see this, so this is 5 by 10 plus 6 by 10 plus 6 by 10. So this is 5 plus 6 plus 6 is this 21? This is 6 plus, this is 17, sorry. 17 divided by 10, this is correct. So this is 1.7. So in here, if you see, I added these coefficients over here. Okay, so these are called weights. I can call these as weights. Okay, and I am adding them. So I can call this thing over here as weighted sum. This thing can be called as weighted sum. So this is weighted sum. So over here, if you see the average I computed, normally if I compute the average, so what I am doing is I am doing something of this sort: 1 by 10 multiplied by 1 plus 1 by 10. This is not 1 by 10, sorry, this was how many? We had 6. So this is 1 by 6 multiplied by 1. 1 by 6 multiplied by 2 plus 1 by 6 multiplied by 3. So I was doing it all together. So I was at the end just dividing it, divided by 6. So this thing over here, if you see this, so this is unweighted. You are not weighting, you are just giving constant weight. Okay, so you are giving constant weight 1 by 6, 1 by 6, and then adding these numbers. Okay, this weight is dependent on how many, let's suppose, how many outcomes you had, or how many of these data points you had in there. So in this case, what I am doing is I am just clubbing them together. So I clubbed this, and this. Then I am adding some weights over here. Okay, and this weight is dependent on how much frequency is there in the whole data. So it was 5 times out of 10. So I gave 5 out of 10. So this was 3 out of 10. This was 2 out of 10. Then I just gave these numbers. So if you see, this average also came out to be 1.7. And when I performed the average, like 1 plus 1 plus 1 plus 2 plus 2 plus divided by whole number of observations, it also came out to be 1.7. So these are two ways of looking at it. One is weighted sum, and there is weighted sum, but the weight is constant. That weight is not variable. So weighted sum basically where weights are variable. And here, if you saw in the first case, you just took a constant number and multiplied it throughout with all the numbers. Okay, so this is the core of expectation. This is how we'll compute expectation, this weighted sum. So what is average? Average can be thought as a weighted sum. So don't you see some strike similarity between this and PMF? So in PMF, what we have is probability that X will take, let's suppose, value 1. So how much frequency is of 1 there? So how frequently do you see 1 in the data? How frequently do you see 2 in the data? So based on that, you construct PMF. But you know that I don't have the complete data. I have the income data with me, based on which I compute the probability distribution. Okay? And now I'll have to compute expectation for that, because we have data is limited to me. I cannot compute the exact average or exact mean or central tendency. Okay, this is actually central tendency. I should write over here. When I'm saying summary, so all of these things average, this gives me central tendency. What I can expect, usually the example that I gave of the weather. So I said, now if you see probability of x is equal to 1, so you can think it, what frequency is there, what percentage of frequency, or how many times does this one occur in the whole distribution. So you accordingly give these probabilities to it. Okay, now you don't have whole data, you can also compute expectations. So how to compute expectations now is, expectations can be again thought of similarly, because you have in discrete case, you will have values x1, you will have values x2, you will have values x3, and so on. So you just consider these things as the values and their probability as their weights. So probability of x1, so you can write like this, probability of x2, probability of x3, probability of x3, and so on. So you can just add these things together. So this will be called as expectation of x. And this x1, x2, and this probability number, they are called as weights or probabilities. That's why I said you can think probability as mass. Okay, that's why we are weighing that mass. Okay, you are having these weights, so these probability will be as weights, and these x1, x2 will be the coefficients, that basically the numbers. That's what we did over here. So this 5 by 10, 3 by 10, 2 by 10, this actually is some sort of probability. Why? If you add these things together, all of these things will be non-zero. 5 by 10 is non-zero, 3 by 10 is non-zero, 2 by 10 is sorry, not non-zero, it is non-negative. So if you see 5 by 10 non-negative, that is greater than or equal to 0. And if you add all these things together, if you add this, it will be 1. So 5 by 10 plus 3 by 10 plus 2 by 10 is 10 by 10, that is 1. So similarly, in this case, summation of probability of xi's should be equal to 1. And this is weights, and this x1, x2, x3, this will be coefficients, that is basically the values that the random variable takes. So this is how we define the expectation for discrete random variables. So this is for discrete random variable. Any question on expectations? The first question asked was, what is this x? This x is not speaking about any value. So this x is the whole distribution. So this is speaking about whole distribution. The example I gave is, let's suppose you have a company in which you are giving salaries. So salaries can range, let's suppose, from 20,000 to 20 lakh. So this is, let's say, 20,000, and this is 20 lakh. So this can be something of this sort. Let's suppose this is probability mass function, or if it's a random variable, this is a probability distribution. This is a random variable, continuous random, this is a probability distribution function. Now what I'm saying is, so if you have to ask a single question before joining the company, you probably want to ask, what is the average salary in the company? So you are not worried about the whole distribution. If somebody is not giving you the whole distribution, that's all right. But if somebody just gives you one number, which will give you some expectation, because if you consider yourself, okay, I'm an average employee, I'll get an average salary at least. Okay, so if somebody says that you will get 1 lakh of average salary, 1 lakh is the average. Okay, so this x here represents this whole distribution, but this expectation of x represents this 1 lakh. That is what can be expected. The second question was, is it will it be affected by outliers? Yes and no. So if you see, these are weights. So this probability, they are weights assigned to the numbers. The outliers usually will have very less weight. Okay, so they will contribute to this expectation very less. Okay, if you have an outlier, let's suppose outlier's value is some 100 and its probability is 0.0001, because that's what outlier means. So outlier will be very less occurring, or its frequency will be very less. So because of that frequency, it will have very less probability. Its weight will be very less. So it will not bring expectation high or low. So because it's outlier, so it is prone to, if you have, let's suppose, couple of the outliers, now they have very huge values, and even if the probability, let's suppose if an outlier has this value, if there is an outlier which has this value, and even if its probability is only 0.001, still it will make an impact. That's why I said answer is yes and no. It can also impact, it cannot impact, but this is the only way we have at the moment. So expectation at least gives you a ballpark figure. So usually in the data we remove the outliers. When you are doing the machine learning, in mathematics also, so outliers will have an impact, and it depends what type of outlier it is. Okay, now let's do some questions in order to nail this concept, in order to at least get the solidified foundation about this expectation. Let's suppose you are a contestant. Okay, you are going on a quiz. You are a contestant. Let's suppose your name is A, and you are going to play a quiz. So in the quiz, there are two questions, question 1 and question 2. Okay? Now the quiz has rules. So if you attempt question number 1, okay, if you got it correct, then only you will be allowed to attempt question number 2, or you can do it other way around. You can attempt question number 2 first. If you got it correct, then only you will be asked to go to question number 1. Okay, you will be only allowed to answer next question given that your previous question that you answered was correct. If you answered it wrongly or the answer was incorrect, you won't be allowed to answer it, the next question. Let's suppose probability of getting the first question right is V1. Probability of getting the second question right is V2. Okay, this is the probability. These are the probabilities. Okay. And now you will let's suppose let's consider this not V1 V2. These are no probabilities. So let's consider this P1 P2 probabilities. P1 P2. P1 is the probability of getting question 1 right, and P2 is the probability getting question 2 right. So V1 and V2 are the money. So this is dollars. This is the money that you will get. Let's suppose if you answer the question right, so you will get question 1 right, you will get V1 If you answer the question 2 right, you will get V2 If you answer both questions right, you will get V1 plus V2 Okay. So now the question is, what is the order that you should answer the questions in? In which order you should questions in? And what is the expectation? What is the expectation of winning? How much can you win based on this probabilities? The question goes like this. So which question, because he has to choose the ordering. So which question should he attempt to answer first so as to maximize his expected winning? So he can choose to answer Q1 followed by Q2, or he can choose to answer Q2 followed by Q1. Now if you see this question, now there are two possibilities. I can either attempt question 1 first, or I can attempt question 2 first. Now for both of these, I can calculate the expectations. If I attempt the question 1, there's an expected estimated. If I attempt question 2, there is an expected estimated. In question 1, I can either win 0, that means on the first question I got it wrong, that I won't be allowed to move to the next question. With what probability? This probability will be 1 minus P1, because P1 is the probability I'll get the first question correct. That means 1 minus P1 is the probability I'll get it wrong. So if I got it wrong, I'll get $0. Now I can win V1. That means I got the first question correct. So with what probability? I'll get it with probability P1. But second, I can get it wrong. That means with 1 minus P2, I can get that wrong. That's why I stopped at V1. I just got V1 for the second question. I got it wrong, and I was not able to get the V2. So in other case, I can get V1 plus V2. I got both the questions right. That is with probability P1 multiplied by P2. So this is if I attempt the question first. So if I just multiply these things and add them together, I multiplied and added them together. So this is the expectation. So this over here is expectation. Expectation of Q1. So if I attempt question number 1, so this is the expected amount of winning. So now similar treatment can be done for the question 2. I can win $0, I can win V2, or I can win V1 plus V2. So this with probability 1 minus P2. If I got the second question wrong, and if I got second question correct but the first question wrong, that is P2 multiplied by 1 minus P1, because I got the first question wrong on the second try. So this is P2 P1. So again, if I multiply these things and if I add them together, so this is expectation. Oops. So this over here is expectation. The expectation when we attempt the second question. So this is the expected amount of money that we win. So these are the both expectations. Now we have to compare both of these expectations. So now you can see this term over here, the term I'll be enclosing in red box, this and this is pretty similar. Not pretty similar, they're exactly similar. And this is 0. This I can cross off these two things. Now the deciding factor is these two things. So we have, in the first we have V1 multiplied by P1 into 1 minus P2, and in the other thing we have V2, P2, 1 minus P1. Okay. Now these are the deciding things. So if we take a concrete example and see which question should we attempt, so we should know 4 values. We should know this V1, P1, V2, P2. So let's suppose we have given probability. So we have question 1, we have question 2. So probability will get it right is 0.6. Probability will get this question right is 0.8. So in this 0.6 case, we are getting $200. And in this case, let's suppose we are getting $100. Okay, some people will think I will attempt this question, so I should attempt because it has more dollars in here. But if you see, the probability is less. Okay, so this result also might seem counterintuitive. Why? Because you are getting $200 here and you are getting $100 here, almost getting double money. So in the first case, you are getting almost double the amount. But the probability, if you there is a very slight difference in probability. So you are having 0.8 and you are having 0.6. There is a 0.2 difference in probability. But when you compute expectations by using these two things that we just computed, so you'll clearly see that you should attempt question 2 first. Why? Because if you compute the expected, you will get expected amount here 400, you will get expected amount here 300. So it is better to answer this question 2 first. I gave a generic answer like this, and you just have to plug in these values in order to come to these conclusions. But if you are given this game, let's suppose, and you ask this, so many other people will choose this because they feel I am having almost double chance of winning. That is, I have double money that I can win here. But if you see probabilistic things, so here we have 0.6 and 0.8. That makes a huge difference in expectations. Any questions on this? This expectation, if you see, so world always, as I said, is uncertain. So that's why the expectations come from. So if you have something concrete, if you have some data which you look at, and then you can make concrete claims about that thing. Let's suppose that data is exhaustive. By exhaustive, I mean you have everything in front of you. As I said, let's suppose you have 2, 3, 1, 2, 3, 4, 5, 6, something of this sort. So if I say what is the average number in these things, so what you can do is you can just sum these things up and divide by the number of observations. You can come up with the average of this. So I'll say that it is 7.5. 6 plus 1 is 7. 7 divided by 2, this is 3.5. Okay, and I just remember from this, just a digression, a problem was given to Gauss. So when he was, I think, 10 years old, he was bugging his teacher so much, and he was asking weird questions to his teacher. Then a teacher asked him, okay, do one thing, can you do the sum 1 plus 2 plus 3 till 100? The teacher thought that probably Gauss will take some amount of time in this, so I'll be busy doing my work till that point. I'll keep these kids busy. So what Gauss observed in this, he said, if I see this sum, so that time probably AP was not discovered what arithmetic progression is. So what he said is, in Gauss did it probably in 10-20 seconds. So he said, if I see this number 1 and 100, so this sums out to be 101. So if I see this 2 and this 99, this also sums to 101. If I see this 3 and 98, it also sums up to 101. So he said, I just have to basically compute this repeating pattern. So if let's suppose I have 100, I have 2 and 99, this is also 101, this is also 101. So if you see, now this 101 has to be summed up. How many times? Half the number of terms. So how many number of these things were 50? So 50 by 2 times. That's 25 multiplied with this. So this is, I think, 5050. So this is the answer he came up with. So because it was an arithmetic progression, and you know how to compute the sum and divide by something n into n plus 1 by 2, something of this sort. I don't know if the formula is right. So but you know a lot about arithmetic progression. This is what Gauss did at the age of 10. Okay, so he came up with this, just a side story. So what I said about averages is, so if you have some concrete data, you can come up with the average. So average tells you the central tendency. You sometimes are not worried about what will be the actual thing that you want. You sometimes just want a number which will summarize the thing. As I said, if you are applying for some company and you want to see, let's suppose I am maybe an average employee, or maybe a much better, maybe a very bit better than an average employee. So you will ask a question, what is the average salary in the company? So you know that salary might go from, let's suppose, 20,000 to say 20 lakhs, something of this sort. So you will see it follows certain distribution. Let's say follow some distribution, maybe this sort of distribution, some tail distribution it follows. And then you will say, if I am an average employee, so that means most of the people maybe they are lying here, many of the people. So maybe I'll get a bit higher salary than this. That's maybe 80,000, 70,000, something of this sort. So this is not telling you anything about the distribution. This is not telling you anything about how the whole data is distributed, but it's telling you the central tendency. You want some expectation. If I, as I also give an example, if I go outside, so right now I live in Bangalore, I may ask somebody, so what can I expect in the month of May? What is the average temperature? What is the average temperature outside in the day? So you may say, let's suppose 30 degrees. So this sets an expectation. If I go outside, I'll expect something. I'll expect 30 degrees to be temperature. But it is not the case that I'll find it outside there. But it's just an expectation which gives me a rough idea about these things. As I said, these are summaries about distributions. So sometimes it's not necessary you define a PMF. So PMF usually gives you everything. PMF gives a distribution, but sometimes you just want a one number summary or two number summaries. You want expectation, you want variance, or you want some other numbers which will give you some rough idea about the distribution, so that you will take decisions based on that. And in the real world, it's not possible to know the distribution always. So, but it is possible to know the average things. So usually, you know, the average temperature in winter, let's suppose in Kashmir, is around 5 degrees centigrade. So you know it's colder there. It also goes to negative temperature, it also goes to positive temperature. But you know that in the winters it will be colder. You have a rough idea. You don't know the whole distribution, but still you have a rough idea. So then I said there are different ways of looking at it. So as I took this number, so this is how we find the average. So if we have to find the average, you sum all of these things up and then you divide by the number of observations. So let's suppose now I had something of this sort: 1 1 1 1 and 1 2 comma 2 3 comma 3, something of this sort. Okay, let's suppose one more 3. Now I can again do the similar thing. I can again sum these things up and divide it by the number of observations to get an average. So I can say these are 5 ones, this is 5, and this is 4, and this is 9. So how much is this? So this is 5 6 7 8 9, and this is 18. I think this is 18 by 10, something of this. This is 1.8. okay, I hope so. 5 plus 4 is 9, 9 plus 9 is 18, 18 by 10 is it 10, 5 2 7 7 3 10. Yes, I think this is 18. So I can do it in one other fashion. So here I can dissect it like this. I did something of this sort: 1 by 10 multiplied by 1 plus 1 by 10 multiplied by 1. So I kept on doing it till 3 by 10, till this 1 by 10 multiplied by 3. So this is basically sum all of these up and divide by number, or divide by this number of observations. That is what came out to be 1.8. So this I said, if you see all of these, so these are things, these are weights, but these are equal weights. These are equal. All these weights are equal. Okay, so I just called this is a sum, but this is not a weighted sum because I don't have separate weights over here. If you see this, so this again is some sum, but I just multiplied it with some coefficient. What if I do this? So what if I club these things together? I have 5 ones, okay, and I have 2 2s, I have 3 3s. So I can write it like this: 5 by 10. Okay, this is some weight I'm assigning to 1. I'll say multiplied by 1 plus I have 2 2s, 2 by 10 multiplied by 2. I have 3 3s, 3 by 10 multiplied by 3. Okay, if you sorry, let's suppose if you do this now, if you compute this thing, you will again come up with the same number. You will again see that your average comes out to be same. So this is 5 by 10, this is 5 by 10, this is plus 4 by 10 plus 9 by 10. So you'll see that this is 18 by 10. Again the same thing. But if you observe this thing more now, if you have a little discussion on this, so these things again are weights. Over here, this is a weight, this again is a weight, this again is a weight, but these weights are different now. So now this is a weighted sum. Why weighted sum? Because you are giving different weights. If the weight was similar, then we don't consider them as weighted sum, because weight given was similar to each of the term. But now in here, these things were given weights. Okay, so this yellow terms are weights. This over here we said this is a weighted sum. Why? Because we assign it weights. Now if you see, these weights have a particular property. So the first property they are non-negative, and the second property is they sum up to 1. So can't we think these weights as probabilities then? So if you observe this thing, this is the first thing is 0.5, the second thing is 0.2, the third weight is 0.3. So these are the 3 weights. Consider this as W1, W2 and W3. So can't I say that these are probabilities, because I can see this property there. I can see that they are non-negative and that they sum up to 1. So I can say these are probabilities. I can assign this P1, I can say this is P2, I can say this is P3. This is like probabilities. And one more thing, so if you see over here, so there are multiple observations which we are clubbing. It is like a random variable also. But you see this, so that's what I said. Mathematics people, they try to abstract all the details. If you now see, I can say I have a random variable x, which takes value either 1 or 2 or 3. Now you can clearly see it. This is a random variable which takes 3 values: 1, 2 or 3. There are only 3 observations possible. You can either observe 1, you can observe 2, or you can observe 3. So there are 3 observations possible. I can say this is my random variable. Then if I have to assign it PMF, so how can I compute PMF? I'll say probability x is equal to 1, probability x is equal to 2, and probability x is equal to 3. So these numbers I have previously computed. The first thing is 5 by 10, that is 0.5. This is 0.5. Oops. Always gives me some trouble. This is 0.5, this is 0.2, and this is 0.3. Now you can see this. So I went from numbers to the to again the random variables. That's how random variables are defined. So now this is a random variable, and this is the PMF, probability mass function of these things. Okay, and over here now, if I want to see the average, how I compute the average. So consider these as now x1, x2. So consider these observations as x1, x2, and x3. Okay, let's suppose one is x1, x2, x3. So how can I define average? I can define average like this: x1, then I can say probability p1 plus x2, p2 plus x3, p3. This is how I defined the average, how I computed the average. But now this is in terms of data where we have incomplete information. You don't have complete information. So what you call this thing is expectation of x. X is a random variable, which we previously saw. And then, so if you see now, I had this variable x. I defined this variable x. So this x could have taken value x1, x2, or x3. So this is the random value. So in this particular case, this is a discrete random variable because it took values small x1, x2, and x3. And now I showed you one way of looking at these probabilities. Okay, these weights can be seen as probabilities. Now this expectation of x can be written like this. Okay, so this is what is the meaning of expectation. So this is actually an average, but when you have these random variables in which the data is incomplete, we call this expectation. This was a bit of revision that we did in the previous session. Any questions on this? Any questions? Okay. After this discussion, let's have a question first so that it will remind you something of expectation, and then we'll move ahead. The question goes like this: a school class of 120 students. So there are 120 students. They are driven in 3 buses. There are 3 buses which are driving them. Okay, for some performance. So there are 36 students in one of the buses, 36 students, 14 in another, and 44 in third bus. So this is the distribution: 36 in bus 1, 14 bus 2, and 44 in bus number 3. So when the buses arrive, so one of the 20 students randomly is chosen. So when these buses are arriving, so they're arriving for the performance. So one of them is chosen randomly. One of them among these 120 students is chosen randomly. Let x denote the number of students. So let x denote the number of students on the bus that randomly are chosen. So this is the random variable x. So what is this denoting? X is denoting the number of students on the bus which are randomly chosen. So you have to find expectation of x. So I think we have a question before that. Yes. So we have 120 students who are in 3 buses and they are being driven to some performance. And now 36 are in the bus 1, 40 are in bus 2, 44 in bus 3. Okay. And now when these buses arrive at the performance, let's suppose, now we have to choose one student randomly out of these 120 students which are in the buses. Let this x denote the number of students on the bus of that randomly student is chosen. So this x denotes that. So x denotes the number of students on the bus of that randomly chosen student. Find expectation of x. You have to find the expectation of x. I'll write this in words. So here x denotes number of students on the bus of that randomly chosen student. Okay, because you are choosing a student randomly out of these 120. Now this x denotes is a random variable and it denotes the number of the bus from which the student basically was chosen. Can you now compute the expectation of x? Okay, let me just go through the question once again. So you have 120 students, they're in 3 buses, they're going on a performance. And once they go there, once a student is randomly chosen out of these 3 buses. Okay, out of these 120 students, and he will be in any of the 3 buses. Now let's suppose x represents here the number of students on the bus from which the randomly student is chosen. So this is that x. Now we have to find the expectation of x. First we should understand the meaning of the expectation of x. What is the meaning of expectation of x? So this means, so what is the expectation that the number of students on the bus will be, let's suppose, what will be that number from which the randomly student was chosen. So this is the meaning of expectation. So how do we compute that? Now you see this x is a random variable. It can take value 36, 40 or 44. This is how we define this random variable. It can take 36 students, 40 students or 44 students based on the number, the students that are in the buses. Buses can be demarked by A, B, C or 1, 2, 3, however you like it, or without demarcation. You can say that a bus containing 36 students, 40 or 44 students. This is the value this x random variable can take. Now, again coming to the definition of expectation. What I said, expectation of x. If it is a discrete random variable, how can you write it? So you write, let's suppose, x. You write x of I, and then you can say summation of I goes from 1 to k. Let's suppose if it takes k values, or if it takes n values, 1 to n, xi, p of x takes xi value. So this is one formula, or you can directly say, and a random variable, then probability mass function. P of x, probability mass function. So this basically means you multiply it, and then you can write it succinct way like this. So if you have to expand it, it basically intrinsically assumes that you have to sum it up. So now here you have to compute this probability of x is equal to 40, probability of x is equal to 36, probability of x is equal to 44. So how to compute this probability? Because now you know there are 120 students. You can say 40 divided by 120. This is 36 divided by 120, and this is 44 divided by 120. So this is the probabilities. 120 students, out of these 40 are in one bus, 36 are in the bus, 44 in the bus. Now in order to compute the expectation, you just have to multiply this xi. So xi over here is 40, it is 36, here it is 44. Yes, multiply these things and add them up. Okay, so when you do this, so you come out to be a number, this number comes out to be 40.2667. Okay, so when you multiply these numbers and add them up, so this comes out to be this. Now we can see one peculiar thing over here. This number is not 40. Okay, because why am I saying this is not 40? Because average over here is 40. If you say 120 upon 3, that is 40. But this is not 40. This is not average exactly then. Okay, then what is it? Okay, the average number on the bus of students, this is 40. That this shows the expected number of students on the bus which is randomly chosen is larger. So here if you see, this is larger. This is 40.2667. This is greater than 40, a little bit greater than 40. Why is it so? So why is it so? Because here when you choose a student, there is high probability that the student will be chosen from this bus. Okay, that's why I said there are lies, not me, Mark Twain. There are lies, Campbell, and then there is statistics. Okay, so usually this is the problem with here. So here the probability which got assigned to this, because it was a little bit higher number, the probability assigned to it was a bit higher. So when we added that, the expectation was a bit higher. Okay, this was not average. So now you can clearly see that. So, and this is a general phenomenon sometimes. It occurs because more students are on one bus, and that is more likely to be chosen. Because let's suppose if I made this very drastic, if I made this something of this sort, 2, 5 and 15, something of this sort, or maybe let's suppose if we respect numbers 120, so I can say 100 on this bus. Then we have 15 and 5. This is bus A, bus B and bus C. Now if you compute expectation, compute the expectation of this. This will be 5 by 120 multiplied by 5 plus 15 into 15 by 120. Can somebody do the calculations for me? Plus 100 into 100 by 120. Can somebody open up the calculator and do calculations? So here this comes out to be whatever this is 85.41. So this tells you that expected number is this. Okay, the expected number on the bus that we choose, because we have high possibility of choosing this bus. Okay, that's what this is saying. So this is not exactly like average. If somebody says me average number of students on the bus, then average is computed differently. But here you saw clearly that when I changed these numbers, I said A is equal to 5, B is equal to 15, C is equal to 100 now. So I made the distribution quite tail distribution. So now when I compute the expectation came out to be 85.41. That is the number of students on the bus from which the randomly student was chosen. That is 85.41. So this is not average. So this here, we gave the number almost around equal. So you saw that the average number of students and the expectation is quite different. The expectation shift towards the number which has high possibility, because here there is a very high chance of selecting this bus. There's a very high chance of selecting this bus, because here we have only 20 students and here we have 100 students. So obviously when you are choosing one student out of 120 students, very high chances that you will be selecting the student from this bus. Okay, and then you will see that expectation is this. On that bus it will be 85, but it's higher number bus basically. Okay, I hope this makes sense to you. Any questions on this? So now if I assume that you have understood expectations, so now we'll compute expectations of some random variables. So we have seen a lot of random variables. We saw Bernoulli random variable, we saw binomial random variable, we saw hypergeometric random variable. Let's try to at least compute the expectation of the random variable. What can I expect? So this is random variable. Why are we even learning about these random variables? As I said that there are a lot of phenomena in the world which do follow this pattern. So in Bernoulli, I said you can see that a lot of phenomena in the world either get successful or they have a failure. And then people try to abstract the detail out. They said, okay, let's denote x as a random variable which takes two values, 0 or 1, failure or success or something like that. So now let's compute the expectation. What can I expect in these distributions? Okay, the first thing obvious is Bernoulli random variable. So Bernoulli has the parameter p, that is the probability of success. This random variable takes two values. It takes either success or failure. It takes values 0 or 1, success or failure. So now it takes success with probability p. Now if I have to compute the expectation of this. So how I can compute the expectation? I know the formula of expectation is x1 p1 plus x2 p2, and I know there are only these two values. I could have extended for the k values, but there are only two values possible here. So what I can do is 0 multiplied by 1 minus p plus 1 multiplied by p. Okay, this is failure because in total the probability should sum up to 1, and that's why here I can also mention it as q, but 1 minus p is also good. So this is 0 plus p. So expectation of x is p. So in Bernoulli random variable, so in this Bernoulli distribution, you can clearly see that the expectation is p. This is called as fundamental bridge. This is called as fundamental bridge. Why this name for it even? This is so simple, but you will see that this bridge gets used multiple times in order to prove other things. Okay. So even if I say, let's suppose if I take an example, so let's suppose we have an x event. If it rains, 0 means it will not rain. So I can write something of this. I can say that x rains with probability, let's suppose p of a. This is my probability. So I can say e of x, a means it will rain. So with 0 it will not rain, a dash it will rain with probability this p of a. So now you can see that e of x is equal to p of a. Similar thing which I said over here. So this is p. Now let's go to the second distribution. This was pretty easy, but I said it has deep implications. We'll see how deep implications can be understood from this. So we'll now second see a binomial distribution in which we have two parameters. The first parameter is n, number of successes, number of trials, and then p is basically the probability of each success. Now you have binomial random variable. It is the independent repetition of Bernoulli random variable, as a flip of the coin or defective pieces. We did a problems on that. We did a lot of problems. So here these things are parameters. Now again you will have to compute expectation of this. So if we let's suppose want to compute PMF, the PMF is probability x is equal to k. So this k basically means you want k successes out of these n successes. How to compute that? So you will say n k choose n. So you are choosing k out of the n, and then you know the success probability is this much, and failure probability is 1 minus p, and this is n minus k. You can denote it by denote this also by q. So you can also equivalent write it nk so as to shrink the notation q and minus k, and here you will write 1 minus p is equal to q, something of this sort. Okay, this has also been discussed, and how do we arrive at this formulation? Pretty easy. And now we want to find the expectation of this. We want to find expectation of x. So why this x is sampled from binomial random variable in which we have n trials, and we have p, a probability of success for the trial, for each trial, which each trial in here is a Bernoulli random variable, and the trials are independent. Now in order to compute this, you have to find this. So what you can do is, you can see that this, because I know that x takes value k, because I have this PMF, and I'll say this k multiplied by n choose k, probability of success and probability of failure. Now I have to do it for all the k's. So k goes from 0 to suppose n for all the k's. So here I took this PMF for one value, but you know that it can take values, it can be 0 success, 1 2 3 4 till n successes. So that's what I did here. So this is what I have to compute. Okay, this is pretty tedious looking, by the way. Okay, yes, questions, go ahead. This is what we have to compute. So over here, this is what we want to compute. The expectation of x will be, so take k and find its probability, plus if that, because that k will have different values. Now it will be 0 by 0 1 2, as I said, gave the example. Let's suppose you have n is equal to 10, that is you have 10 trials. You can have 0 1 2 values, that random variable can till 10, 0 success, 1 success, 2 success till 10 success, and each of this will be associated with some probability. It will be p0, it will be p1, p2, something of this sort, p10, and then you multiply them together and add them up. So that's how we wrote this k. K can take different values from 0 to n, and each of these things is associated with this probability. This is probability mass function, PMF, that we saw. Now we have to simplify it. So that's where our story proof will come into picture. So if you remember this k and choose k, this was evaluated, because I don't like this k over here, because this is dependent. I want to take it out, but I can't take it out of the summation, because this summation somehow has k into it. But if you remember the story proofs, you know that this can be written somehow, some different way. We have n people, in which we have to choose k people, and one is the precedent. So how can we choose? So you choose k people out of n people, and then out of k people you choose one precedent. This can be written like this also. You choose let's suppose among the n people you first choose a precedent, So once you choose the precedent, that's n ways. Then you are left with n minus 1 people, and out of those you have to choose k minus 1 people. So this is equivalent. Okay, this is the story proof that we did. And if you want to prove it algebraically, good luck. You can prove it algebraically also. It will take a couple of pages, a lot more thinking, a lot more shuffle of terms here there, but story proof is quite nice, quite easy. Just remember this: we have n people, we have to choose k people out of them, and out of k people we have to choose one precedent. It can be written like this or this. So here I can substitute now, because I want to get this k, I want to get rid of this k because I don't like it, I want to take it outside. So now expectation of x can be written as something like this: k goes from 0 to n. Now I can substitute k and k with this n minus 1, k minus 1. So I got rid of this k over here. I can just pull it out: pk 1 minus p n minus k. That's why I showed you those story proof. I showed you one Remote's sum, one Remote's convolution also. That's also by story proof. And then I showed you this proof also. So now if I take this n out, so I want to take this n out and I want to take one of the p's out. So what I can write is, I'll say, I can even start this k is equal from k is from 1 also, or from here, because k is equal to 0 will be 0 and it will multiply with 0. That won't make sense in the sum. I can start this k from 1 also. So I'll say n, I'll take one of the p's out. Okay, what I'm left with from k is equal to 1 to n, and I'm taking this n out. So this is n minus 1, k minus 1. Now I took one of the p out, so this will be p k minus 1 and 1 minus p n minus k. Everybody with me so far? If you are following this, so what I can do is I can substitute. Let's suppose I want this to be j. Let's suppose I substitute j is equal to k minus 1, something of this sort. So what I can do is np, because j is equal to k minus 1. So I'll say summation of k is j plus 1. So I can substitute j from here. So j is equal to, say again, 1 to n. So now n minus 1, and I put this k minus 1. I substitute it with j. Okay, then p. So k was substituted. K was substituted. This should not get in the middle of the proof, because I'm losing hold the chain of that thought. So now I'm substituting this k minus 1 with the j. So that's what I'm writing over here. So p, now I can substitute it with like this. So I have to convert it into j. So this is j is equal to k minus 1, and then k is equal to j plus 1. So this I can write j plus 1 over here. And then I can write 1 minus p. This is n minus, and I have to put k. So this k is equal to j plus 1. So this will be n minus j minus 1. Okay. So this again over here is simply 1. Why? Because you can see it is binomial theorem. Okay. This is something of this sort. So this is x term and this is y term. So if you add these two probabilities up, this will be summing up to 1. Okay. So this thing over here, if you evaluate it will be equal to 1, because j plus I, if you see n minus j minus I, if you delete this, so it will be you will be left with n. Okay, and then it will cancel this out. So this will be equal to 1 if you expand this thing up, not just this thing, whole of this thing will be equal to 1 with the summation terms up. So this is the binomial theorem. If you have x plus y to the power, let's suppose something to the power n. So let's suppose these two things sum up to 1. So x plus y sum up to 1. So it is, let's say, 0.8 plus 0.2 and to the power n. So this is equal to 1 to the power n. This is equal to 1. So this is what over here. So p and 1 minus p. These two things, if you add these things up, it will be x plus y, and this will be going like this, and it will be 1 to the power n. This will be that p plus 1 minus p to the power n. So you know that the sum is 1, and then sum is 1. Basically, whole of this term will go into 1. This is equal to np. The expectation of x when x is a binomial random variable is np. This is the expectation of the binomial random. Okay, so over here, if you see, there were two mistakes. So initially we mistakenly wrote this j is equal to 1, but this j should actually start from 0, because we put j is equal to k minus 1. So if j was 0, if k was equal to 1, so that basically means j should start with 0. So this is over here. Okay, then we mistakenly also wrote j plus 1 over here, but this should have not been j plus 1 because it was k minus 1. So k minus 1, when we put j is equal to k minus 1, so directly it should be j over here. It should not be k minus 1. So these are the two simple mistakes that we did, and we sort of ignored these mistakes, but now this is in the correct form. So this is actually the expectation. So I was more concerned about this sum you should get as 1. So this whole thing over here, you should get it as 1 by using the binomial theorem. So if you are watching it, then you can do it as homework. As I said, the hint is x plus y to the power n should be equal to, if this x plus y is equal to 1, so if x plus y is equal to 1, so then I can write 1 to the power n is equal to 1. So this actually is in the perfect form of this x plus y to the power n. And exactly, you can see here it's n minus 1 in this case. Okay, and then you can just substitute p and 1 minus p, you will get it as 1, and then you will get the expectation NP. Now the question is, what is the meaning of this expectation of NP? So intuitively, what does it mean? So what I said is, if it's a binomial process, so binomial process can be, let's suppose if factory is producing some items, it can be defective or it can be good. Items can be defective or good. If it is a review can be bad or good. So all these processes producing a review or you having a defective item in the factory, so these are binomial process in that thing. So what I said is expectations and NP. So what can you expect? If somebody says the success probability is 0.7, so you can say what I can expect is, I can expect 70% times I'll get a better thing, I'll get success. So that is pretty evident when we drew those graphs. So in that, if we had, let's suppose, had 0.7 success, so I said that you will see that distribution is centered around that 0.7. So you will see distribution something around this centered over 0.7. That is, if we have this, let's suppose 10 reviews, so you'll have 7 good reviews and you'll have 3 bad reviews. But it does not tell you that other things are not possible. Sometimes 10 reviews is also possible, sometimes 0, but it's very rare. But if you see what will happen frequently, what will have high probability will be having of this. So you'll have this distribution peaked around this point. You'll have 7 good reviews and 3 bad reviews, because you see expectations NP. This is expectation, tells you what is the tendency. So what can I expect? So in the binomial processes, like that of if you are having a company and you're producing some products, and if you want to see, that's called quality control. If you want to see how many pieces are defective and how many are good, so because that's a binomial process, you can clearly say that I can expect this NP. Give me the probability of success, I can tell you what can you expect. If you give me 0.7% as a success probability, I can say the 70% items will be good. Similarly, in terms of reviews, so this perfectly makes sense because all of these are binomial processes. But this, you should be very careful. You should not extrapolate it to other processes also, because sometimes the phenomenon might not follow binomial process, and we'll have high tendency to say, oh, probability is 0.7. That means 70% probability. No, it only is the case when it is a binomial random process. If it is some other process, we'll have to see accordingly. Now I showed you one tedious way. So there was a clever trick that I did over here. So this is very clever trick over here. So if I did not show you the story proof from going this step to this step, I just wanted to bring this N out because I knew it is NP. So if I didn't knew it, it will be tedious for me also, because I knew somehow I'll have to come bring this K out, and I'll have to bring this NP. I'll have to make it NP. And this was some sort of trick which I knew, and I showed you this. But if let's suppose we did not have this, then how to do with this? Okay, and then we'll go with indicator random variables, which we also have seen using a lot. But here I'll again assume one. I'll introduce 2 things, but I will prove them later maybe. So expectation actually has this linearity. Okay, so I'll write that thing over here. So I'll write linearity of expectation. Linearity of expectation. So what is that? We'll give you a formal proof in the subsequent sessions, but here I'll just write the definition of that linear expectation. So if you have, let's suppose, something of this sort, you have expectation of 2 random variables x plus y. So what linearity says is, so you can compute the expectation separately and you can add them up. Okay, and this is equivalent. If you combine these 2 random variables and compute expectations, or you compute expectation of x plus expectation of other variable and you combine them, then this is equal. Or it is sometimes also written like this. So you have expectation, you have c multiplied with into that random variable, and this is equal to like this. So this is how linearity is defined. So we'll prove this. So this is applicable if these x and y are dependent or independent. This is in both cases. So this expectation linearity is a very beautiful property of expectation. So we'll use this property with the random variable, with this random indicator variable. So now if I say something of this sort, you have this e of x. So can't I break this into indicator random variables? So what I can say e of x can be written as something of this sort. I'll say e of x1 plus e of x2. So each of this plus and so on till e of xn. So each of this xi is an indicator random variable, while it will be either successful or it will be either failure. So you know that what is the probability. So I know expectation of this is bridge, that fundamental bridge. So here this is by indicator random variable. So from here I can write it 1 0. So this is by fundamental bridge. I know this is equal to p if it's successful with p, or if it's failed with success with probability q. So if I have this n event, so this is n and all of this have probability p by fundamental bridge. So you can clearly see this is np. You can just n, but each of this is p plus p plus p and so on. So I can directly write it np. So here I can say this is by fundamental bridge. Okay, I just introduced one random variable. So this is again a story, something of a story. So each of this trial can be thought as an indicator. It will be successful or it will be a failure. Okay, now because I know expectation is linear, okay, I could have not done this if expectation was not linear, because I know that E of x, so this is sum of all these indicator random variables. Now I know that I can expand it by using the linearity of expectation, which I just said over here. You can believe me on this if this follows, but I'll give you the proof in the next session, and this is a pretty clever proof and pretty easy proof. Any questions on this?